All right, thank you, and yeah, I'm going to talk about SerenityOS. Yeah. Sorry, need to set up the recording, but anyway. Right, SerenityOS, hobbyist operating system, and how many of you have heard about SerenityOS before? All right, surprisingly many of you. For the rest of you, this might be initially a bit weird, but I'm trying to convince you that SerenityOS is not weird at all. It's a great platform to learn about operating systems, how they work under the hood. It's especially interesting if you are interested in Linux kernel. SerenityOS is a Unix-like operating system, and although it doesn't share any code with Linux kernel, it shares a lot of ideas. Before we look into it, a bit of history. SerenityOS was started in 2018 by Andreas Kling. Andreas had worked at Apple in the WebKit team there, and after resigning there, he was looking for something to do, and yeah, he started this ambitious project to build a new hobbyist Unix-like operating system. For the first couple of years, he worked on it himself, but then over time, initially through Reddit, it gained attraction, and now it's a healthy community, hundreds of contributors in GitHub, Discord server with thousands of members, and yeah, you might have seen Andreas's YouTube channel, which is sort of the key thing which I believe attracts most people to the project. All right, let's take a look at it. So, those of you who have used, for example, Windows operating systems pre-XP find this very familiar. It has this kind of a vintage grayscale look to it, kind of a boxy design, no transparencies, a lot of drop-down menus, so this kind of a nice vintage look and feel to it. It has your typical your applications, your browsers, your file managers, and I'm sorry, by the way, it's a bit small, but scaling the thing with QEMU and SerenityOS, it's a bit of a hassle, but anyway, hopefully you can see it. And you have your utilities, office tools, your basic tools. Of course, there's the paint program and so on. And then the Unix part of it, which is the terminal. So SerenityOS is mostly POSIX compatible, or it has good POSIX compatibility. It means a lot of things. Pekka mentioned about POSIX in his presentation, and it means that, for example, a lot of common utilities you're used to in your Linux kernel shells, they are here. So that's your typical, the shell is very familiar to you if you're using Mac OS, your Linux distribution, whatever. Okay, and yeah, let's dig into the code. We can take a look at more of the features in the later in the presentation, and you can come after the presentation to test it out on my laptop if you want to. Let's dig into the code a bit. So I have here the SerenityOS Git repository. And if there is a never definition of a monorepo, SerenityOS is it, because all the applications you see in my QEMU there, the kernel, documentation, building the thing, all the libraries, they are all in this one monorepo. So whatever you see in when you play around it with, get some stack trace, try to figure out how something is implemented. It's all in this one repository, so learning how it's implemented, it's really easy. No need to scroll through any other repositories. That means that also that standard libraries, C standard library, all the libraries are custom made. SerenityOS doesn't have, well, basically no third-party code. Makes it very easy for us who want to learn how operating systems work, Unix-like operating systems work. All right. On to today's assignment. So we'll be implementing this Aurajoki application, and it will be a very simple application. We'll just show the uptime of our operating system, time since boot. We won't be making any fancy UIs this time, just that which now says to do, get the uptime information. And I have here, this is now, I've cloned the repo. I have made some boilerplate here. This is the main of the Aurajoki application. It's SerenityOS, mostly C++. And yeah, there's the main. This builds the UI. We won't be going through how the UI is built. We just mostly we'll be just looking into the sort of getting the uptime here. But just for you to know that there is a, well, again, custom library, custom way how UIs are built in SerenityOS. And we want to get that uptime information. This is the placeholder we saw already. So we need to fill it with the uptime information. In SerenityOS kernel, there's a class called time management, and it has this uptime information method, exactly what we want. So we can just access it, right? And just modify the code a bit. So again, to save some time, I have made here some boilerplate. So let's just call it kernel time management uptime milliseconds to see what happens. Let's try to, I'll stop the QML running, try to build it with the Ninja build tool, see what happens. We got errors. We got a lot of errors. And we got errors because of multiple reasons. Firstly, what we are trying to do here doesn't make really that much sense, because we have this user space application, this Aurajoki application, and we cannot really, the kernel isn't just some kind of a library that you can link or include to our user space application. The kernel is its running thing, and it actually is running our user space application. So it's sort of the wrong way around. We cannot import or include or link the kernel to our user space applications. And the second thing is, of course, we cannot read in our user space applications that applies to your Unix distributions, probably all operating systems that your sophisticated operating system you are running. We cannot read kernel memory in user space mode. So let's maybe step back a bit here and define some of these user space and kernel things I'm talking about here. So presumably most of us here do some kind of web development. We create our backend application with Python, Node, whatever. And we develop those locally. We develop those to serverless wherever. So our applications run in sophisticated operating systems like your on top of your Linux kernel in protected mode. And as user space protected mode applications, we have a limited view of the operating system resources. That is, we have a limited view, of course, to the process memory. We can access only our process virtual memory address space. We cannot access any I/O devices directly. We need to go through the kernel. Yeah. So the kernel and ultimately, actually, the CPU protects us from doing whatever we want as user space applications. We need to escalate our privileges to kernel mode, or actually, to be a bit more precise, what we need to do is that we need to hold our user space application running, then move the execution to the kernel where we can do anything, read the kernel memory. In our case, we want to read the uptime information. We need to give kernel the control to do its thing, and then return the execution back to the user space. And SerenityOS is fully supported by x86 64-bit architecture, so that's your Intel CPUs. That again makes this a bit more easy to learn how SerenityOS works because we don't have Linux kernel has a lot of CPU specific stuff. SerenityOS kernel doesn't have that much of that. So anyway, so we need to in x86 terms we need to escalate our privileges from so-called ring 3 mode to ring 0 mode. So from user space mode to kernel mode. So how do we do that then? We do that, of course, with system calls. And when we're developing again our applications in our day-to-day jobs, we do these system calls, of course, all the time. There's, of course, a lot of multiple abstraction layers between us and the system calls. System calls we do for memory allocation, for reading I/O, connecting your databases, reading files, all kinds of things where we want to get some privileged protected information out of the operating system. And to explore the system calls a bit more in detail, we'll be actually making a new system call, custom made for getting our uptime information. And we'll be stealing this from Linux kernel. So SerenityOS doesn't have this sysinfo system call, but Linux kernel does. And here we have a nice spec what we can implement. So system call named sysinfo. It has a sort of an interface API, the way to pass the information back from the kernel space to user space, kernel to user space with this sysinfo structure. And it has the very interesting member for us, which is the uptime. All right, let's implement this. And again, I have made quite a lot of work related to that, just to save some time. So first of all, in the kernel API, the system calls can also sort of be thought about the APIs from our user space applications to the kernels, roughly. Anyway, here's the structure which we use to pass the information from the kernel back to our user space application, back to our Aurajoki application. It has the uptime member. I omitted the rest of the fields just to make it a bit simpler, right? Then the actual implementation of the system call. I have again made this pretty far along already. This looks a bit weird. Not that many lines of code though, so let's digest this a bit. So first this weird thing, $, sys, whatever. Then the name. Then we take as an argument the sysinfo structure we just took a look at. This had the uptime member. All right, it's an argument, interesting. Then we initialize here. This is now in the kernel, of course. The sysinfo structure. We set the member with the uptime thingy we tried to do in our Aurajoki application already, but it crashed. It didn't compile. By the way, if we would be able to somehow access that time management thing from our user space application, so if we would, somehow figure out the memory address where that time information is, just try to read it. Can somebody know? Does somebody know what would happen? Similar thing would happen in your Linux kernel operating system. What would happen? We would get a famous fault.
Segment fault?
Yep. We would get a segmentation fault, so we were accessing an invalid memory segment where as a user mode application we cannot access. Exactly. Thank you. So in order to not get that segmentation fault, here we need to run this in kernel mode. We'll get back to that in a bit. But anyway, let's continue. So we fill in the uptime information, right? Assume that it works. Then a debug line. Then we have this weird thing, copy the user. It takes as a first argument the thing that the pointer we passed in here, and then it takes a reference to that thing we just created. All right, and then we return 0. So this is probably not how you would implement this in your day job. You would just probably return something, but system calls are actually, they have a very strict calling convention, and they need to be implemented in this very well-defined way. First of all, why we cannot just return this thing here is, of course, again, we cannot read kernel memory when we call this from our user space application, but we must copy the thing to the structure which is located in the user address space or in the process virtual address space. So that's why we pass it as a pointer, so we can copy the thing, whatever we do it in kernel. We copy it back to the user space structure. If we would take a look at this sysinfo implementation in Linux kernel, it would be quite similar actually, in relative terms at least. So Linux kernel, for example, has this very same function named the same way. So copy stuff from kernel memory to user space, so we can access it, right? And then we return 0. That's just an error code. So we return a success error code with 0. So anyway, let's now see how these are called. So in your Linux distribution and as well as with SerenityOS, system calls are wrapped. In your Linux kernels, those are wrapped using, for example, glibc, muzzle, and as I mentioned, SerenityOS has a totally custom standard C standard library implementation, or in this case C++, but anyway, and here we wrapped those system calls. There's the user space correspondent of the thing, which we pass it as a pointer, and then something that makes it just a bit easier to call. And there's the interesting part here is the actual invocation of the system call. So first argument here is this weird thing. It says sysinfo, but it's actually the value is a number, so it's an enum. So for some reason we pass to this syscall invocation a number. All right, that's interesting. And then the second is just the reference to the thing, the user space thing that we saw as a first argument in the system call implementation. So, all right, a number then. Let's now dig into the details. So, all right, now we're in a scary place. Okay, so I'm sorry this is grayed out. I haven't set up my editor correctly, but here you can see some assembly code. So these system calls are indeed very, very foundational on how operating systems kernel work together with the CPU. So syscalls have in x86 64-bit architecture actually a dedicated CPU instruction for invoking them. That is aptly named syscall. And we pass, I'm looking at the wrong function here. So we're actually invoking this one, and we set to a set CPU registers the number of the system call and then the memory address of our argument. So again, this doesn't really explain why do we call those with the numbers. But of course, when you think about it, since we cannot from user space, this is called from user space, really know where that sys, in our case, the sysinfo system call is implemented, we need to defer those with something, and we defer with those with numbers. And this works exactly the same way as in your Linux kernel. So system calls are referred with numbers, and there's a system call table up here. It's defined like this. This is a table, really looks a bit weird, and in the place 135 there is the sysinfo syscall somewhere. We'll get back to this system call table in a bit. All right, let's finally call this system call then. So I need to comment those out so we can compile it, and let's see if Copilot can help me. Not quite that. Yeah. And let's try to build this now. Not quite.
You're missing a column.
All right.
No column down.
Oops.
At the upside.
It may be now correct. All right, while it's building and installing, we can then try to figure out what happens next. So now we have done everything that we can in our user space applications. We have digged down to the very bottom. We are now really close to the hardware. So we have invoked that syscall CPU instruction. What happens next? Well, next the syscall invocation actually moves in x86 our CPU mode to kernel mode. That basically means we can do anything. We can execute the kernel code. So that doesn't still yet answer how does the kernel know that it should now take control. Let's take a look at that. One of the very first things we do when we boot up our operating system, that is SerenityOS, your Linux kernel, whatever, we set up the entry point for system calls. So when that system call is invoked, then the kernel knows that, hey, this address, it checks from the CPU that now I need to execute the system call entry point. All right. So now we have called the system call. We know the entry point. The kernel starts executing the code, and let's take a look at it. This is even more horrifying code, even more assembly code. So what this essentially does is that we save our user space application state or stack. So our Aurajoki application save is sort of halted. Its CPU state is saved. This is what this thing here then does. Next up is actually executing the system call with the system call handler. Take a look at that in a bit. And once we have executed our system call, we have written all the, for example, in our case, we have written the sysinfo structure to the address space where address location where our user space application, so our Aurajoki application read it. Then we just restore the application execution back to our user space application. So as simple as that. This can be seen as a sort of a context switch. Usually what is meant by context switch in operating system terms is that we change the execution from thread or process to another. But here we actually change the context from our user space application to kernel. Right. And somewhere bottom down here this is then exiting the system call, meaning it sets the CPU mode back to the user space mode, so we cannot read, or we cannot read, get our sort of privilege level back in place as in user mode. One last thing, syscall handler. So there's a lot of stuff in this syscall handler, but this is the interesting part. So there was this number 135, which is the sysinfo system call number in our case. So here is the thing that this function here is actually just the number 135, and we check from this system call table, which is again initialized as one of the very first things we boot up our operating system. We look up from that table the core system call, its address where that function is located, get the arguments, and simply call the system calls after multiple checks, sanity checks, and so on. But that's your system call for you. I went maybe to way too many details, but just wanted to show you that these system calls are a very fundamental thing on how operating systems work. And me as a sort of web developer could figure out quite well how these work using SerenityOS, following the code, and yeah, and also too lazy to write slides, so better look at the code. But anyway, let's see if we have now finished or does it work? Maybe. Looks reasonable. It doesn't say to do anymore. It might not be a surprise to you that there is already an existing implementation of uptime. And there's a shell utility. Uptime would print out the same information for us. Let's take a look actually how that's implemented. As a usual utility, what it does, again, very simple application. It opens a file in path syskernel uptime, reads its contents and prints those out to standard out. So it reads a file. So everything is a file in POSIX or kernel file systems, right? And what that means is that there's this thing called virtual file system defined by POSIX or Unix, whatever. And it means that behind these virtual file systems, there can be multiple implementation of actual concrete file systems. And those can be disk-backed file systems like your ext4s, your NTFS, what have you. And then there are these so-called pseudo file systems like sysfs in this case. And these pseudo file systems are not backed by physical disk, but by rather kernel state, so to say, kernel memory. So unsurprisingly, there is nothing in SerenityOS that periodically writes the uptime information to any disk-backed file, but rather this is a file we generate when we call it. So let's take a look at that file. This is the file actually. And when we open the file, we see the same familiar figure here, so we call the time management. So instead of having to write separate system calls for each and every whatever device, whatever information you're interested in your operating system, you can use the common open, read, write system calls to access, basically read bytes and then interpret those as you will in your user space applications. Another example of those are, of course, your devices. So I can show you an example in SerenityOS. This again works really similarly. I think this uptime information is actually in the proc file system, at least in the Linux kernel I checked. It was in the proc file system, which is again similar to sysfs file system. So pseudo file system access basically kernel state. Again, these device drivers, as you know, your devices are files or can be accessed with the file system or I/O system calls. So what we are looking at here is the Windows server, which all the UI applications, like our Aurajoki application, is a child of this Windows server, and they get access to mouse and keyboard events through this Windows server and its event loop, and reading mouse and keyboard state is of course with opening files and reading their contents. All right, I think this is about it for my presentation. Again, went into a lot of detail here, but I think my point here is that, well, I've read about operating systems, well, quite a lot over the years, and reading about the stuff only gets you so far, and I think actually tinkering around, hacking stuff here, for example, messing about with the device drivers, trying to change somehow how your mouse works, for example, is truly the best way to gain the real understanding what's happening, how operating systems work. I showed you here a couple of fundamental things on POSIX Unix-like operating systems, and yeah, I recommend you trying out SerenityOS. It's easy to build. Compiling the kernel doesn't take too long, and yeah, that's it.